Hi there, this is Penelope. This is a short video in a pair of videos giving a very quick overview of what calculus is. So we start off this video with differential calculus. Where statistics and probability is the mathematics of chance, you could say that calculus, differential calculus, was the mathematics of change. Now, Newton did a lot of work on this, so did Leibniz. He was trying to work out actually how an apple falling from a tree was different from the moon not falling from the sky. But that's another story. What we've got is, if we've got a straight line, that's something like that, and it is straight all the way along, what we can do is we can work out how y changes with respect to x. And what we do is we take any point A and any point B, and we compare how this change is compared with the horizontal change. Now, you know that almost certainly as the rise over the run, and we call that the gradient, and often it's referred to as m. Now, for a straight line, the gradient will be constant. For the sort of curves that Leibniz and Newton were looking at, it was much more tricky. They were looking at curves like that, where the slope is definitely not constant. The slope's not even the same all the way along the curve. So what they were faced with was a big problem. Now, what they could find was the slope of a tangent to the curve, like that. Well, maybe they couldn't, because what they've got there is just the one point. So this gave them a bit of a problem, because they couldn't find the rise over the run, because there wasn't an A and a B for them to work with, as there is in the straight line case. Now, we already know a little bit about basic trigonometry. So we know that with a circle, we can again draw a tangent to the curve, and it's only going to touch it in one place. But again, how are we going to find the slope of that, as there's only one point of contact? What we could do is think about what might happen if we take lots of lines that are parallel to this tangent and think about what might be happening. So here's 1, 2, 3, 4. These lines are seconds. What might be happening to the whole situation as we're moving from a secant up here, number 1, right down to the tangent? If we look at the length of the chord cut off by these secants, and as we're moving from secant number 1 down to the tangent, we see that the length of the chord is becoming shorter and shorter, and eventually here the length of the chord is 0. So we can kind of understand that, because it's something that we already know. Now, Newton and Leibniz, who were the two guys doing this some centuries ago, applied this logic to the original position of being able to to find the slope of a tangent to a curve. Let's start with a curve something like this. And suppose we want to find the slope at a point. So we start off with a chord that's cutting it like that, and it's between a point X. Now, if we're just going to go a little bit along to this point here, some texts call this distance h, and some call it delta h, just meaning the change in x. And this is a function called f of x. Then this point here, we've moved from x to either x plus h, if that's how you want to call it, or x plus delta x. We need to find, because if we're going to find the slope as being the rise over the run, we also need to find the y coordinates. At x it will just be f of x, and at the point of x a little bit further over it will be f of x either plus h or plus delta x. So in this case then we can find the rise over the run. It would be f of x plus delta x minus f of x over, now this distance from here to here is just delta x. Now, well, we don't want that. We actually want the slope of a tangent. We don't want this big gap in here. We want delta x to be very small. It can't be 0 because then you'd be trying to divide by 0, but we can think about what happens as it gets closer and closer to 0. So what we can say is, well, we can think about this in the limit. So let's call this m of the tangent. So the slope of the tangent would be the limit as delta x gets towards 0. We can't have it as 0 because then we can't do that. We can't divide by 0. But we can imagine what happens as it gets very small. Now, this now is going to be a function. It's not going to be a number. So this is what we call the gradient function. And we'd also call it the derivative. Now, it's in terms of delta, Greek letter for d, so we would write it as d, and fx is y, by dx. So that is, we call that the derivative. And the process that we've used to find that is differentiation. Now, there's books and books and books on calculus. We're not going to go into it in very much detail. Even in the maths course, what we do is we say for a basic function, if y equals ax to the power of n, then the derivative of that, this is the gradient function, and this is just a rule, would be n ax to the n minus 1. So we're talking about a rate of change. This is too complicated to do every time. So what we've got is we've got these lists in books and we look them up. This is probably the most common one, but you need to find one of those lists to give you the list. You also need to be able to find the derivative if what you've got is a function times a function. So you've got a product. So you'd use a rule for finding the derivative of a product. If you've got a function divided by a function, then you've got a quotient. So there's a rule for finding the derivative of a quotient. We can even find the gradient function or the derivative of a function of a function. And for that, we use the chain rule. So if you search my YouTube channel, you will find videos on the product rule, or the quotient rule, or the chain rule. So that just gives you a little bit of background about what it is, this calculus, this differentiation stuff.